Oh, we're on. Well, it doesn't say that we're on. Hello, hello. Jack, first in, as always. So it looks like you've left. Hi, Jack. Good morning. Look at all the people. Ooh, 5 people already. Yay. I'm just trying to figure out how I can look at the chat on my phone. Oh no, Jack. I don't really understand. It's not in comments. My channel. 7 watching live. Why can't I see chat on my phone? Oh no. Oh, there it is. Out with my dog. Harry, it's been a long time. I seem to get more people joining from last year. Why are you shouting at me, Harry? Hi, Joanne. I'm good, Harry. It's going well. How's it going with you? There's quite a bit of lag. Woohoo! Physics at uni. Harry, you can tell everybody how awesome physics at uni is. Yay. Everybody should do physics at uni. Well, everyone who loves physics, which is everyone. It's good, lads and ladettes. Do it. Is George here? I can't remember who Holy Pigford is. Is that Elliot? And the boss cat is Max. Good morning, Max. Hello, Ruben. Right. 14 people. Whew. I can't see who's watching. I can only see participants in chat, which is a bit weird. It is Elliot. Good work walking your dog, Elliot. Right, should we start? I need to put that somewhere I can see it. Hello, Tom. Good day, good day, good day. Right. Shall we begin? Vincent, Owen, hello, hello, hello. Everyone's here. All the cool kids anyway. Woo. Well, that's fine, Elliot. I'll talk everything through. Right. Have I got a nice pen in the right colour? Brush size 2. Okay, so we're going to start talking about scalars and vectors. The nature of scalars and vectors. So both of them are quantities. Scalars have magnitude, and vectors have magnitude and direction. So both are quantities. So scalars are quantities with magnitude, and vectors are quantities with magnitude and direction. And it says examples should include. So if we've got scalars and vectors, well, I can do straight lines, can't I? So we've got speed is a scalar, velocity is a vector, mass is a scalar. So these are all the ones you absolutely have to know. Force is a vector, and weight is an example of a force. Acceleration is a vector. Distance is a scalar, and displacement is a vector. Now, these are scalars and vectors in this topic, really. Obviously there are more. So energy is a good one. That also appears in this topic, and that's a scalar. For our second years, potential is always good to remember it's a scalar. So you always add it, you don't add and take it away. Other things that are vectors, momentum is a vector. Anything essentially that can cancel out. I don't want this colour. That's better. Anything that can cancel out. If you think one's going one way and one's going the other, and they cancel out. So things like forces, velocities, accelerations, displacements. That's really all there is to talk about in terms of the specs of scalars and vectors and examples of them. You may well be asked in a multiple choice question or in a longer answer question how many, to name 2 or 3 vectors or scalars, or to say which of these are in the right columns for the multiple choice question. So you need to remember these. Just trying to think if there are any other favourites, but these are the ones that pop up in mechanics. So now we need to talk about addition of vectors by calculation or scale drawing. So if we're doing calculations, then we're going to be limited to 2 vectors at right angles. So let's say I walk north for 1 kilometre, and then I walk east for 2 kilometres. So my actual displacement, I wonder if this will work. No, that won't work. My actual displacement would be like this. So this is a displacement north and a displacement east, but then when you add them both together, you get a displacement which looks like that. Now, if we want to add them together, we pop them tip to tail, and in order to find this displacement, let's call this S, that one, I can do Pythagoras. So S squared equals 1 squared plus 2 squared. So S equals the square root of 5, which is a really awkward number. I should have put nicer numbers, but that's okay. So if I miss the voice. Hi Morgan. Hi Jess. Jess, I don't understand. Do you mean my voice? Oh, I need to be careful because I'm going down below the screen. Into my picture. I can't write down here because you can't see it. I'll get rid of that. So it's only going to be two vectors at right angles, but if you're going to do scale drawings, you might have vectors at angles other than 90 degrees. You may well then need to do SOHCAHTOA for this. So let's get rid of this. And don't forget that I can rub out everything. It's because you missed my voice, of course. Oh no. Oh, there we go. So if we've got, I'm going to move this triangle around a bit, I think. I don't know. Oh. Rowan's watching the stream. Physics. We might need to find a direction. So if I've got my 1 kilometre, and I'm going to do it this way, and my 2 kilometre, actually we could do it as a bearing, couldn't we? So if I've got my 1 kilometre, I could just do it down here, stupid. I could find this angle as a bearing from north. So if I've got the opposite side and the adjacent side to that angle, tan of the angle is opposite over adjacent. So theta, which is the angle, in this case it's going to be a bearing, is inverse tan, opposite the angle which is 2, and adjacent the angle which is 1. So tan to the minus 1 of 2. Nice. If we're doing scale drawing, I normally ignore scale drawing because I don't like it, but you're going to actually have to have a protractor and a ruler in your exam, so you can draw I don't know, 2 vectors, and we'll join them tip to tail. Let's say these are displacement vectors again, and they go like this, and they give you, say, an angle from north, and then they say this one's east, and then say this one has this bearing. They might give you bearings like this, but it's not that important. As long as you can describe the direction adequately, then it doesn't really matter which angles you're using. In this case, I join my triangle, oh, it's not a triangle, is it? I join my shape tip to tail, and that would be my resultant displacement. But you're going to want to measure this. So if that one was 4 meters, 3 meters, 2 meters, you use the protractor to measure your angle. And then you could scale a scale of 1 centimeter equals 1 meter, and you draw it like that, and that line will be 4 centimeters long, that will be 3 centimeters long, that will be 2 centimeters long. If you're doing a scale drawing, they're going to want to see a scale. like this. Scale drawings, they could ask you anything, because they can give you angles and distances, and they could ask you more than 2. But for calculations, they're only going to ask you 2 vectors at right angles when you're adding them together, which is neat. There's quite a lot of stuff here. I'm going to have to rub some more things out. I need a bigger brush. I'm a bit confused. I can't seem to keep the chat on top on my phone, which is a bit weird. Oh well. So if I'm resolving a vector into 2 components at right angles to one another, maybe I start with a velocity which goes like this. And I can actually resolve this into any 2 components I like, as long as they're at right angles to each other. So what I could do, but I won't, because it would confuse me, I could do this one here, and this one here. Oh, that's way too long. And this one here. That would work 100%, no worries. But chances are you're going to want to be working in vertical and horizontal components, or you want to be at least putting your components in a way that they make sense. So if this is a velocity, this is velocity v, and there's a projection at an angle theta, then your horizontal component, I'm going to use subscripts of x and y, that's going to be your original v multiplied by cos theta. So these 2 lines, again, the angle's getting cozy with the 2 lines, so that's going to be cos. And then if I'm thinking about, I mean, you can add these via the parallelogram rule, you can think about that. Or you could think about moving this line over here, and then it would be the opposite. So this one over here would be Vy, and that would be the original V multiplied by sine of the angle. Which is right. If you're doing IB, then you get these in your data book, which is nice. If you're doing A-level, then you just have to remember or figure that out. Examples should include components of forces along and perpendicular to an inclined plane. Well, that's a tricky one. We'll talk about that one. I'm just trying to think of an easy way to remember this, but there's no real easy way. So I'm taking this as the hypotenuse of my triangle, and then if I'm trying to find this side here, then I know that cos theta equals my adjacent over my hypotenuse, but I know the hypotenuse, so the adjacent, which is what I'm trying to find, is the hypotenuse times cos theta, and the same for sine theta. That's opposite over hypotenuse, but I'm trying to find the opposite, so I get h sine theta equals the opposite side. So do you need a protractor in the exam? Yes, you need a protractor for both exams. Velocity can be modeled in polar coordinates. I don't think so, Jack. Really? You have to show me that question, because we don't do polar coordinates. Yeah, definitely take a protractor. If they ask you to do a scale drawing, you'll need it. Otherwise, you won't. But you don't want to be throwing away easy marks on scale drawing by not having a protractor. Right, let's do this inclined plane business because it's a bit tricky. I'll have to get rid of all of this. Sorry. You can always rewind or watch again at a later date. Hope everyone had a good Easter. Lots of chocolate. I didn't get much chocolate because I'm old, but it's quite good because I'm supposed to be training for a triathlon. Oh well. Right, let's draw an inclined plane. Looks like a wedge. And then on my inclined plane, I'm going to have a box, because boxes are easy to draw. Now, if we say that the box is on an inclined plane which is frictionless, that old chestnut, then the only force, there should be only a couple of forces acting on the box. And we draw them from the centre of mass of the box. So this is the weight of the box, which is the mass of the box multiplied by the acceleration due to gravity. And then we have a normal reaction force from the surface. We'll call that capital R. It could be N or Fn or all sorts, but we'll stick with R for now. So those are the only forces acting on the box. But if there's no friction, the box is going to be accelerating down the slope. So what is it that's causing the box to A, not jump off the slope, B, not fall through the slope, and C, accelerate down the slope? Now it can only be components of the weight. So when we draw this triangle, we're trying to make it so that we've got a component parallel to the slope, which is going to look like this, and a component perpendicular to the slope, which is going to look like this. Now this angle theta is the same as this angle theta. Now we've got two components here, so what we're doing is we're resolving our vector for the weight, so the force, which is the weight, we're resolving that into two components. We've got this one here where the angle's getting cosy, so that one's going to be mg cos theta. And then if this was a vector triangle, this one here, the component which is parallel to the slope, would be the opposite side, so that would be for sine, so that would be mg sine theta. Now, it's not quite straight. Now my reaction force and the weight, the component of the weight which is perpendicular to the slope, are going to have to be equal. So we can say that R equals mg cos theta. And then the resultant force acting down the slope is mg sine theta. So actually the acceleration down the slope, so if f equals ma and this is f, we divide both sides by m, and g sine theta would be the acceleration down the slope. If we had friction, if the box was in equilibrium, which might mean that it's moving, if we have friction, which is normally f subscript f, then that, if we're in equilibrium, so either the box is stopped or the box is moving at a constant speed, we're going to have our friction is mg sine theta. Oh, no, not in A-level physics. So much physics, Sasha. You do love it. I promise. Okay, so we've talked about calculating vectors, we've talked about resolving vectors, and now we've resolved a weight which is always going to be the longest side of this triangle. The biggest mistake people make is making this side too long and then having this side horizontal. We don't want that. The weight is the force, the real force, the actual force, so that's the one which is going to be the hypotenuse. These two components of that force must be smaller, because if we add this force and this force, we have to get this. So that one's good. Problems may be solved either by the use of resolved forces or the use of a closed triangle. So if we're talking about resolved forces, it's very much like this. You get, so say I've got a free body with a force acting like this and a force acting like this. Say it's something suspended by I don't know, let's say 2 ropes, and it's got a weight. So we've got a tension T and a tension T. Now we can resolve our forces into x's and y's and add them all up, which is what I would tend to do in this situation. I'm going to do my components like this. Whoop. So that force so this force up here, where should we have an angle? So if we have this angle here, then this force is going to be T sine theta, and T sine theta is going to have to equal mg. If this was well, let's say this was T. No, let's say they're the same. So we're going to have T sine theta from both the two tensions. If these were identical length ropes and this was in the middle and all that stuff, we'd have identical tensions. It can be more complicated. You could do it with T1 and T2, and you could solve simultaneous equations to find what you need. But so the vertical component here would be the sum of the vertical components of the tensions in both the ropes. The horizontal component for each one would be T cos theta, and we know that that would equal T cos theta because it's not moving sideways. The one we're interested in this case would be this one. But if we had different T's, then, so if we had, no, because I can't change that. If we had T1 and T2, then these two would be different. And this would be T1 sine theta plus T2 sine theta. And then you could make that equal to mg, rearrange, and substitute a la simultaneous equations. It's not so much detail I can go into today. Use of a closed triangle. So if I've got forces, let's check again. So let's think about this case again. If I've got this situation, then let's get rid of all of this. And I want to solve for a body in equilibrium. So anything in equilibrium, if you add up all the forces, they equal 0, which means if you put all the forces together, they make a closed triangle. So this is going to be T, this is going to be T, this is going to be mg. Now, we've had lots of discussions about this in the physics department. Is there any such thing as not a closed triangle? No. But to stay safe, I would recommend writing closed triangle. That's what they want you to call it in the spec. So we'll stick with that. It could be a closed polygon. So if I had lots of forces, all acting in different directions, well, that's only 4, but as long as when you draw them together they make a closed shape, that means that body is in equilibrium. This is all for forces. The same for other kinds of vectors. Conditions for equilibrium for 2 or 3 coplane forces acting at a point. Appreciation of the meaning of equilibrium in the context of an object at rest or moving with constant velocity. So equilibrium means that an object is either at rest or moving at a constant velocity, but it's a weird one. So equilibrium means that the thing has constant velocity. If v equals 0 meters per second, then it's at a constant velocity. So it's at equilibrium. All of these things would be in equilibrium. So if this was a mass hanging from 2 strings with tension T each, and it was in equilibrium, all these forces made this closed triangle, and it wasn't accelerating, then there would be no velocity. If we had a situation where we had something moving and it had a free body diagram with a driving force and a frictional force, so that thrust maybe, and then friction. If these two are equal, it would be in equilibrium, but it doesn't mean it's stopped. So we can have dynamic friction or static friction, which we don't really go into in AS or A level, but we do in IB. But you can have either of these. You can have this in motion or not moving. So if you were pushing something and it wasn't moving because of friction, then it would be in equilibrium still, and the thrust would equal the friction. But if you were moving and you were pushing something and the drag or the friction had equaled the thrust, then it could still be moving at constant speed, and it would still be in equilibrium. So the sum of all the forces acting at a point equals 0. So for equilibrium, and we'll talk more about forces in a minute, we have no resultant force. And we talked about resultant forces. No, we didn't. We talked about resultant displacements earlier. If you've got any kind of system, the ones we were adding vectors, if we were adding vectors and we had something left over, so if we actually got a sum that wasn't 0, then you would not be at equilibrium. But if you add them all up and you get a sum which is 0, so if you've got a closed shape when you add all your vectors up, then you would be in equilibrium whether you're moving or not. I'm still struggling to see chat. Math and physics are so exciting. God, I love you. 10 people. Is this too early in the morning for students? Yeah, there we go. Eating breakfast? Fair enough. Fair enough. I just got a notification to say that I'm live. Woohoo! Right. Shall we continue? Ooh, moments. I like moments. See, I like moments. Yeah, I did send an email out last night to tell everybody, but it was, I don't know, it was quite late. You know how it goes. Right. Moments are turning forces. So forces which are acting but relative to a point. So if I have a Oh, let's do a triangle. So if I have a point, let's call it P, and then I have, let's do the classic seesaw. If I have a seesaw balanced like this, and this is point P, and I have a box on this end, which is a distance away D, and has a weight of W, then I think one of the issues is figuring out clockwise and anti-clockwise moments. So in my head, I think about, here's the point. If I had this side of the point and I made a force in that direction, it would try to move down, but it couldn't because there was a point, so it would start to curve around this way. And that's in the same direction as a clock. So that is a clockwise turning force, or a moment. If I put a wall on the other side, because drawing boxes isn't working out for me today, then it would try to turn it that way, but it wouldn't be able to. Let's call that W2, not W1. It wouldn't be able to, because this one would be balancing it out, and there's a point here. That would be an anti-clockwise moment. We'll call that D1, and we'll call this one D2. Be a good time to talk about the principle of moments. The principle of moments says for a body in equilibrium, one mark, the sum of the clockwise moments equals the sum of the anti-clockwise moments. Going off the end of my little writing pad thing. 2 marks. Ta-da! So 2 marks for the principal moments. For a body in equilibrium, the sum of the clockwise moments equals the sum of the anti-clockwise moments. Now we just talked about things in equilibrium. So if this was in equilibrium, it would either have velocity of 0 or constant velocity. But that would be what we called so constant velocity. That's going to be called translational equilibrium. So translational is it's translating its position to somewhere else. We've probably done translations in maths. It's moving. It's moving. But if we've got a body in rotational equilibrium, that would be here. It means it's not spinning. Probably means it's only spinning at a constant rate, but for us it's going to be not spinning. So in rotational equilibrium, that means the principle of moments is doing its thing. So in this case, our clockwise moment, the turning force clockwise, equals the turning force anti-clockwise, and this beam is going to stay still. So moments are, so you need to learn this definition, the magnitude of a moment, the magnitude of a moment is force multiplied by the perpendicular distance from the point to the line of action of the force. So where we draw the arrow, that's the line of action of the force. If we go from the point here to the line of action of the point, it's the perpendicular distance, it's right angle, that's going to be d2. So we're going to have w1 d1 equals w2 d2, and that would be in rotational equilibrium. It would also be in translational equilibrium, so that means that there's another force here. Let's call that the reaction force at P, and R, the reaction force at P, is going to be W1 plus W2, which is quite neat. So we've got clockwise and anti-clockwise turning forces, which we call moments, and the moment is the product of the force and the perpendicular distance from the point to the line of action of the force. Now, what if it wasn't perpendicular to start with? That's a good question, Ash. Oh. I shrunk this brush again, didn't I? Let's get rid of all this. So let's think of a different situation. I'm going to end up rolling out wrong things in a minute. Let's think of a different situation where I've got a crane with a big mass here, and well, let's have a hanging mass here. So it's force times perpendicular distance from the point, which is here this time, call that P again, to the line of action of the force. So here we'll call that little mg, and then here we'll call that big M G. So these are the lines of actions of the forces. Maybe we know the length of the crane arm, D, but we're not going to be able to do the weight times D, because we're either worried about this distance here, which would mean it would be this is literally what the definition says, the perpendicular distance, let's call that D perpendicular to the line of action of the force. The way I tend to do it is to find the component of the force so say we need this angle here, theta, that would be mg cos theta. I expect that angle to be the same as this angle here. So we mg cos theta times d, or d cos theta times mg, which should give us all the same stuff. So you need to make sure you're talking about the perpendicular distance, and then with this definition you're going to get a mark from force times distance. You're going to get a mark for force times perpendicular distance. So that's 2 marks there for your definition of moments. Oh, getting cramp. If we have a situation where we have two forces which are acting on well, acting around the point. Let's call the, well, in fact, let's call them both F. And then we've got all these different distances. So let's call this one D1, D2, and then this one big D. So the turning force from this force on this end is going to be FD1, and that is an anti-clockwise moment. But this one here is also an anti-clockwise moment. So my total moment is FD1 plus FD2, but D1 plus D2, we could factor out F, factorize F. Never quite sure how that works grammatically. We could do D1 plus D2 multiplied by F. That would give us FD. So the definition of a couple is a pair of equal and opposite cloplanar forces, and the moment of a couple is the magnitude of the force multiplied by the distance between the two forces. So in the same plane, they're equal and they're opposite. It could be on the same position, but that would be a bit boring. If we separate the two forces and make them equal and opposite, then we get a couple which is, I think it's actually tau, the torque if you like. So the moment of a couple is the force, the magnitude of each force, multiplied by the distance between the two forces, which is cool. Center of mass. Ooh. There's a lot of definitions in this topic. You must know your definitions, otherwise it's all going to go wrong. So center of mass . No, it's not only if D1 and D2 are the same. It doesn't matter if D1 and D2 are the same, because they're always going to add up to the distance between the two forces. So the moment is always going to be, so if we do the so if we have that, it's probably going behind my face now. Then it's always going to be the distance, the total distance between the two forces, regardless of what the distances are. So the centre of mass is the point at which all of the weight of an object made a boo-boo through which all of the weight on an object appears to act. So if you have an object, if you want to find, I'm going to do this now. If I'm trying to find the centre of mass of an object, if I put my finger there, it turns that way. If I put my finger there, it turns that way. If I put my finger underneath the centre of mass, it doesn't turn either way. It's best not to do it with a bottle full of water. It's quite tricky. So that's the point. If you have that, if you find that point and you put a force there, there'll be no turning force due to that force. If you have any regular solid, like a square or a circle or some kind of triangle or even a cube, then the centre of mass is at the centre. So you need to know that, so you need to be able to apply that in different situations, like when you've got turning forces and things like that. Interesting thing about moments is if I were to do this sum, so figuring out all these moments and all that stuff about this point instead of P, I would still find the same answers. If I were to do it about this random point here, then I'd have a turning force here, turning force here, but I'd also have a turning force from here, which would be this reaction force. Then I'd still get the same answer. So you can take moments about any point you like and always get the same answer. So if there's one point on your beam or whatever's going on, which you don't know enough about, use that point to take moments about, and you just eliminate it from your equations. Oh, I feel like it's going to be a long one today. I was putting this together last night and I was thinking, oh, there aren't that many sections, should be fine. Each section is quite involved. So the thing with this topic is there are loads of definitions, and then to cap it all off, the application, the questions, they're really hard. Well, not hard, but there's lots of different things that you can be asked. For example, with motion along a straight line, is there more than a bottom? Oh yeah. So let's make a straight line. Let's have, I don't know, a person who runs with their arms out like that. A person running. Nice. So if this person runs and their displacement is 20 meters and it takes them 4 seconds, my average velocity is going to be the change in displacement, so delta S equals 20 over the change in time t, which is 4. So they're going to be running an average velocity of 5 meters per second. Do we prefer blue pen or black pen? Because I normally write in blue pen and I'm thinking, oh, this black looks quite nice. Tell me in chat what you think. So regardless, if this person is changing velocity over this 20 meters, if it takes them 4 seconds, then their average velocity was 5 meters per second. If I've got a changing velocity, now we're only going to have Jack loves black and blue. Ah, that's not really helpful, Jack. If I have an acceleration, it's going to be a constant acceleration. If we're calculating acceleration, it's going to be a constant acceleration. But we may have times where we have non-uniform acceleration. We'll talk about those graphs in a minute. So calculations may include average. So this is an average speed and velocity. The direction, if you're quoting this as a velocity, it would be 5 meters per second right. Okay, let's let's go with equality and diversity, and we'll use black and blue and all the different colours as much as possible. I've got a purple there as well, which I've put on my list, but yeah, I wonder if I do F1 twice. No, it doesn't work. I only get 8 shortcuts for my colours. Anyway, Sash is writing in purple. Let's have a bit of purple. So if I'm quoting a velocity, I have to have a distance, I have to have a magnitude and the direction, otherwise we don't get 2 marks. We want to have 2 marks. If I'm calculating accelerations, I've got a change in velocity over a change in time. So let's say at this point this person's velocity was 4 meters per second, and she gets over here, it's 6 meters per second. Now if I've done maths in my head correctly, the average velocity over this time should be 5 meters per second, but my acceleration is my change in velocity, which we're going to use by a v for initial velocity and a u, no, that's wrong, a v for final velocity and a u for initial velocity. So it's my final velocity minus my initial velocity gives me my change, and that can be negative, over my change in time, which started at 0, so my final time minus my initial time was 4 minus 0. So in this case we get 2 over 4, 0.5 meters per second squared, meters per second per second. Just listening to my son singing upstairs. It's very lovely. He's a very good singer. What am I trying to say? This is going to have to be to the right as well, otherwise they'd be probably slowing down. So we're speeding up to the right. If they were running to the left and they had an acceleration to the right, then they would be slowing down. But then they could slow down and stop and go back the other way, and that would still be all an acceleration to the right. And actually a good example of that is if we have a ball which goes up and then back down again, and the question is, what's the acceleration here? What's the acceleration here? What's the acceleration here? Well, actually the acceleration in all those places is the acceleration due to gravity, which is 9.81 meters per second per second. If we're doing instantaneous speed, we want to start looking at graphs. So let's start looking at graphs. Get told off my wife if I call them graphs. To speak proper. I'm not really a big fan of the purple sash, I'm afraid. Sorry. Right. Uniform, non-uniform acceleration. So uniform means the same. Non-uniform, so uniform acceleration is the same, and non-uniform means changing. So let's do some graphs of itchy nose of some things against time. So let's do displacement against time. Let's do velocity against time. Let's just turn this that way so we can see Rowan making a drink. Anyway, enough of that silliness. And let's have another graph of acceleration against time. Let's start with, I don't know, an easy one. A horizontal line on a displacement time graph. That's going to give me a horizontal line at 0 on my velocity time graph and a horizontal line at 0 on my acceleration time graph. Yeah? So that's for stationary something. If I've got a straight line on a displacement time graph, then I'm going to have a flat line which is non-zero on my velocity time graph. But I have not got any acceleration, so I'm going to have a flat line at 0 again, my acceleration graph. If I have a curved displacement time graph with a constantly changing gradient, that's a bit of a weird one, a constantly changing gradient which is the same. And they didn't let you pass. That's just rude. I'm sorry to hear that, Reese. So if I've got a constantly changing gradient, then my rate of change of displacement is increasing constantly. That would give me a straight line with a slope on my velocity time graph, and this time we've got a non-zero acceleration. Got glasses, yay! Right, hopefully that'll make life much easier. Right, so this is accelerating. Yeah. Now we can do some fun things. Like, for example, on this graph here, well, let's do something else. So for this graph here, the gradient, which I'm going to call m, equals the velocity. So when I had a straight line, or a flat line, my velocity was 0, so that goes down here. And this actually will come up again when we do simple harmonic motion, moving from displacement time, velocity time, acceleration time graphs. So the gradient of a displacement time graph is velocity. The gradient of a velocity time graph is acceleration. We don't have a quantity to describe the rate of change of acceleration, at the very least not in A level. The area under here would be displacement times time, which gives us units of meter seconds, which doesn't mean anything to us. But the area under this one is going to be the displacement. And then, just thinking, the area under here be acceleration times time, which would give us our velocity, I think, if you knew U. These are the ones we're really worried about. If we wanted to find the velocity, so we wanted to find an instantaneous velocity, Rodney, go away. We all met my dog last time, right? And then go meet my cat. This is Rodney. Say hello, Rodney. Hello, Rodney. He's old and dying, and he's attacking me, and I don't know why. Maybe he wants food. Maybe he just wants a cuddle. He's having a nice time. Anyway. Go away, Rodney. We're busy doing physics. If we wanted to find an instantaneous velocity from a displacement time graph, we'd have to draw a tangent to this line, which would be at a point. What? That's fine. It's okay. So a tangent to the line would be where a line that touches this line and the normal is perpendicular to that line. So then we could do the gradient of the tangent, and that would give me, so for a curve, the gradient at a point equals the instantaneous velocity. That's how you'd get the instantaneous speeds or velocities. I'm wondering if I'm actually using this mic or it's using the one on the laptop. Either way, nobody's complained. So let's EG graphs. Who is Jack Pop? Chemistry. Chemistry and physics are equivalently awesome. I'm going to go with. E.g. graphs for the motion of a bouncing ball. Right, let's do that. Why did I rub out all the axes? That was stupid. No, there's no beef. There's no beef between physics and chemistry. Physics and chemists love each other. Sure, I've actually thought about this one before. So we've got S and T, and say
Chemistry is not better than physics. They're entirely equal.
Yes.
I'm watching your live on my phone.
Good. So my displacement would be, so if I dropped it, it would get steeper and 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 steeper. And then it would bounce back, so it would, displacement from the ground would be 0, and then it would get less and less and less and less and less steep, and on and on and on. Probably dropping to lower heights actually. So we'd have it like this. And then, because it's not efficient, not 100% efficient, we'll talk about that later too. For my velocity, I would start at 0, and then I would get faster and faster and faster. So my velocity would be getting faster. Ooh, this is a good one. I'd be getting faster, so that would be going up. My acceleration would be constant as I fell. Well, that would be weird as well. My acceleration would be constant as I fell, so that would have to be a straight line, getting faster. And then as I went up, it would have to be a straight line again, because my acceleration would be constant. At the top it would be 0. And the bottom would be a maximum but be lower, and then that would be 0 as well again. But it'd have to be a bit curved. But then this is a gradient of that, so you'd have 0. Oh no, I'd have to have another 0. Oh. So it'd be 0 at the top. Oh, this is a weird one. And I'd have a constant acceleration. My fastest point would be at the bottom. Then when I turn around, I'd have to go negative in a very short amount of time. And then I'd have constant acceleration to 0. At the top, is that right? Constant, yeah. this point here, so my velocity would get slower, cross 0, and then get faster again, and then where it bounced, there'd be a quick bounce, and I'm not doing it exactly right, and then it'll go back up again to here, and there'll be another bounce. And then for my acceleration time graph, all of these parts here would be constant, and then when I hit the ground, in fact, most of the time I'd have a constant negative acceleration, except when I hit a peak force like this. And every time I hit the ground I'd have a positive force, but I'd have constant acceleration any time I was in free fall. That's an interesting one I'd never thought of before. Of course I've read all of the spec before. Right, so that was the motion of a bouncing ball, which is not very easy. It's much easier if you think about something in simple harmonic motion. But I'd like to talk about a velocity time graph that looks like this. Because then I can say the acceleration, if I've got u here and v here, my acceleration, which is a gradient of a velocity time graph, is v minus u over delta t. And then we can rearrange that one to look like our first Suvat equation. We take that one out there and add u I've lost it now, Jack, sorry. So v equals u plus a t. If we rearrange this, then if I split this into something like that, then I can say that the area under here, which is going to be ut plus, we know that if displacement is velocity times time, then I get the area under there plus v minus u multiplied by t, so that's this height here, and that's times by half, it's a half base times height. Now if I add these together, I get ut plus a half vt minus a half ut. So if I minus half ut from ut, I get s equals a half u plus v all multiplied by t. And that is this one of our Suvat equations. Which is pretty cool. We'll rub that one out and save it for later. Because I then know something about this from this equation here. If I have v minus u, that equals a t. Then s equals ut plus a half a times t again. So s is ut plus a half a t squared. Slightly different. These do appear in your data books. Finally, if we go back to this one, S equals half V U plus V T, and we substitute in for T, so T equals V minus U over A, then I get S equals a half U plus V minus U over A. I can get rid of those two, so I can get 2AS equals, and then if I multiply these out, I get U squared, and I get plus UV and minus UV. What did that get right? Oh, because that should be minus U squared, because I get U times U, but it's negative. So I get V squared equals U squared plus 2AS. And that's our last one. Acceleration due to gravity. These, right, let's talk about how we might solve problems using these. So that's how we find our Suvat equations. And that's from the nature of the graphs of, well, essentially from just the one graph, so the velocity time graph. So these all work for uniform acceleration. So when acceleration is constant. If I want to solve a Suvat problem, I do it like this. I write this every single time. I find out what A is, what V is, what U is, what S is, what T is, and then I choose the appropriate equation. So you're always going to get, more or less, 3 of these. One of them you'll want to find, and one of them you won't know anything about. So if you don't know anything about S, then you're going to want this one. If you don't know anything about A, you're going to want this one. If you don't know anything about V, you're going to want this one. If you don't know anything about T, you're going to want that one. There isn't one without a U in it. Sometimes U is given to you as 0, but you don't always notice. If you do this for all your Suvat problems, when we start talking about projectile motion in a second, it will start to look slightly easier. God, an hour and 20 minutes in. Oof. Oh, Harrison, it's a pleasure to be making videos again, to find the time. I've got my daughter in nursery, and the other 2 kids in the other room. I think they're probably watching. That means that I've only got 7 real people, 6 or 7 real people. Oh yeah. What have I put there? Okay. Jack, that's not in the data book. Acceleration due to gravity G. We'll talk about this a bit later. If F equals ma and weight equals mg, if I have an object in free fall, then the force is mg, and the resultant force equals ma, and the a and the g, oh, not the a and the g, the 2 m's cancel. 2 g's actually cancel as well, and g. So the acceleration due to gravity we call little g, and it's 9.81 meters per second we'll talk about required practicals maybe another time. Maybe in class. We will look through your lab books. Because otherwise this stream is going to be 3 hours long. I'm already hungry. Okay. Didn't expect it to be as long as this, but it's okay. Projectile motion. Now, let's start with the hardest case, shall we? Let's start with this situation here, where I've got, say, a ball. Let's call it a tennis ball. I'd like to go to tennis tonight, but I think it's going to be too wet. I have a tennis ball projected at an angle theta with velocity u. Now, what we can do for our Suvat equations for this ball is I can treat my vertical velocity and my horizontal velocity separately. So this angle's getting cozy in here, so that's u cos theta, and this is u sine theta. And if we use the same notation that we used earlier, that's uy and that's ux. Now you don't have to do y and x, you can put arrows and do all sorts of things, but I prefer to use x and y. Just checking that everything's still on the screen. Not too bad. So this time, when I do my Suvat equations, I have to do s, x, u, x, v, x, a, x, and t. And then I've got sy, uy, vy, ay, and t. Now t, the time of flight, is going to be the same horizontally and vertically. So the t actually links both of these together. Normally, when we're doing these calculations, we treat acceleration as 0. We say that there's no air resistance for projectile, and the vertical acceleration is going to be 9.81 meters per second. In this case, ux is u cos theta and uy is u sine. Woo! Now we've lost it. Sine theta. And you can do all of this before you know anything. It will probably tell you something about the displacements or velocities, or it might be that it's following the path of a projectile, which would be a parabola, where at the top v equals 0, or vy equals 0, should I say. So you might be able to just treat half of it. For this as well, these two displacements, they would be half each, and it would be half the time of flight as well. It's symmetrical on both sides is what I'm trying to say. Yeah. So you can use your Suvat equations independently in both directions. It's important that you remember the only thing linking these two parts is the time of flight. There are other situations as well. So if we had something projected horizontally, then y equals 0 at the beginning. If we have something projected vertically, again vy equals 0 at the top, and then you wouldn't have to worry about anything horizontally. This is another one where the the tricky part is in the problems, but they'll be solvable using the equations of uniform acceleration. It's always going to be a uniform gravitational field, so we're always going to treat the vertical acceleration as 9.81. Aren't ux and vx the same? Yeah, that's right. So if acceleration is 0, then vx is also u cos theta. 100% correct. So then all we need to know is t to find s. Or u, or theta. You're probably given theta, maybe not. This velocity here is going to be the same, but in the opposite direction vertically as this velocity here. So many things. So many things. Are there any questions about... No, Jack, I can't imagine. Are there any questions about projectile motion that people have had from when we've done it in class? I take a sneaky peek at what's going on. No questions? So no questions, we'll move on. Okay. Sensible questions, chat. Well, I've done it again. Come back. Qualitative treatment of friction. So friction acts in the opposite direction to motion and is between two surfaces and is quite complicated, but one way we can think about it is if we've got two rough surfaces and one's trying to move over the other, then it bumps and it bumps and it bumps. There are also other kinds of forces when these things touch each other or get super close to each other. Van der Waals forces, the beginnings of chemical bonds trying to stick these things together. All of that goes to make friction. It's always in the opposite direction of motion. You don't need to know about the difference between static and dynamic friction. It's quite straightforward. Of course, one's stationary and one's moving. Rodney, go away. The qualitative treatment of lift and drag forces. Okay, so you do need to know that if I've got a plane, and my plane is moving, lift acts perpendicular to the wings. I've got a plane with wings like this, then the lift acts perpendicular to the wings. So if my plane is banking, my lift is still perpendicular to the wings. Drag, so drag in air. What do you want? Excuse me a second. Get rid of the cat. Drag drag is another one which is always in the opposite direction to motion, and it can be a whole combination of things. We've got, it's kind of an umbrella term for things like friction in water, friction in fluids. So you're dragging water, dragging air. We can call them air resistance and water resistance. But we can put them under this umbrella, which is drag. Terminal speed's a good one. So if I've got anything that's falling, let's get one of our planes back. Let's say that a supply drop comes out of my plane. I know what we should do. Let's say a supply drop comes out of a party bus. Now, when this object is falling, it's going to start off immediately with V equals 0, and then the drag force, Fd, is going to be 0, or the air resistance. As we get someplace further down here, V is going to be bigger than 0, and my drag force is going to be smaller than the weight. When we get to some point down here, my velocity is going to equal my terminal speed, which is faster than all the other speeds so far, and my drag force is going to equal the weight. So as I'm falling, I'm going faster, and as I go faster, drag forces increase. So friction increases as you go faster, air resistance increases as you go faster. And if you're falling, you get to a terminal speed where the drag force, or the air resistance, is equal to the weight. So then, this is also another example of an object in equilibrium, which is neat. Factors that affect the maximum speed of the vehicle. Let's do that one first. So let's list those. We've got power, shape, that's about it, isn't it really? The fluid you're moving through. For our projectile, we've got a parabola. That's no air resistance. But if I were to have air resistance, then I'd have a shape something like that. Maybe that's a bit too short. Like a squashed parabola. That's when we've got air resistance. And this line is always under the parabola and always shorter. Or the range is always shorter. We call the range the distance a projectile moves. Newton's laws of motion. See, this one looks like a small one, but it's not, is it? So our first of Newton's laws of motion an object at rest or in uniform motion. If you remember, uniform means the same, so this is a constant speed, remains that way unless acted on by an external force. So that's Newton's first law. So if something's resting on a table, it's not doing anything, unless I push it, it's never gonna do anything else. It doesn't mean there are no forces acting on it, because you've got the weight of the reaction force from the table. It just means it's not gonna move without somebody pushing it. It tells us that we need a resultant force to change the motion of an object. So the second law is actually force is proportional to rate of change of momentum, which is weird because it comes before momentum, but if momentum is mass times velocity, then force is mv minus mu all over t. Now, for us, provided that the mass doesn't change, which it won't, we can take m out, and we get v minus u over t, where f equals ma. So this is in a situation where the mass is constant, so not for a rocket taking off, but for most situations, well, all situations that you're going to have to deal with, f is going to equal ma. Our third law, I'm going to say every action has an equal and opposite reaction. But I'm also going to add in acting on different bodies. So if body A acts on B, then B acts on A. And the classic one, the one that I like, is if I've got something and I drop it, then we've been treating it as a projectile with having only force due to gravity. So you think, oh, there's only one force. There's only one force acting on the thing that's being dropped. But there's an equal in magnitude, opposite in direction force from the earth, from the ball on the earth. So this is a ball, then the earth is pulling the ball down, but the ball is pulling the earth up. We don't notice because the acceleration of something that massive would be hugely small. You need to learn those. All three. I am sorry. I do apologise. But, you know, what you got to do. You just got to learn loads of things. And you got to use them to solve problems. It's tricky. Okay, momentum. Bum, bum, bum. So momentum equals mass times velocity. We can use P equals mv. Momentum is always conserved. We call it different things. Linear momentum is the one that we're going to talk about. This means that linear momentum before a collision always equals linear momentum after a collision. It's alright, Minnie. The postman's here and the dogs are going crazy. There we go. So the principle applied quantitatively to problems in one dimension. So if I've got a ball and another ball and one moves towards the other, and then after they collide, let's say that one stays still. In fact, let's not say that one stays still. Let's say they're both moving, and then they're still both moving. They haven't actually shrunk in size. That's just my drawing. We've got VA, VB. Let's scratch that. Let's say we've got an initial velocity UA, an initial velocity UB, and a final velocity VA and a final velocity VB. And then object A is a mass MA, and object B is a mass MB. So we say that MA UA, which is the momentum of this object, plus MB UB, which is the momentum of this object, has to equal MA VA plus MB VB. So the total momentum, we should say total, equals total momentum. The total momentum before a collision has to equal the total momentum after a collision. We can't lose momentum. We can't lose linear momentum. There's a really good video about shooting a block on the side from, I want to say, Vsauce or Veritaserum, the guy with the dark hair, and they shoot a block on the side, and it's like, how high does it go? It's very interesting. You should watch it, but I don't want to talk about it now because it's too confusing. We're never going to have more than two bodies. Sometimes they'll be moving, sometimes one will be stationary. Another situation that we might have is if A and B stick together, in which case they'd have the same velocity. Let's call it VAB, but then their mass would be MA plus MB. That'd be after the collision. We'd still have this before the collision if they stuck together. This would be an example of an inelastic collision. We'll talk about those later. So quantitatively means you're going to have to do sums on it. And second years especially, I think you're essentially going to be tested on everything in the specification. You've got 3 papers, 2 hours each. They're going to ask you about everything, I reckon. Yeah, long papers as well, I think. There's 95 marks, 85 marks. And there's a lot of multiple choice as well, so they can fit a lot of content. Right, we defined force a second ago as equal to the rate of change of momentum. So F is delta mv over t, or delta p over t. And we say we can, it's kind of the definition that impulse equals change in momentum. And impulse, so let's get rid of this. Is there anybody still there? It says there's 8 people watching, but no one's talking to me. This is because no one's actually watching. Because it's so easy. So impulse, let's call it I. It's not really equals delta mv. But actually, if this is delta mv, then F times delta t is the same. Let's imagine we've got a force against time graph. If we have an impact, the force increases and then the force decreases. So maybe it's a tennis racket or a hockey bat hitting a ball, hockey stick hitting a hockey ball. But if we know that F delta T, the area under this graph, equals the impulse. And it equals delta mv. So it says quantitative questions may be set on forces that vary with time, so like this. So impact force is related to contact times. So it might ask you to find the maximum force. It might give you the change in velocity of something that gets hit, and it gives you a graph. It might ask you what happens to the force if it increases the contact time, crumple zones, packaging. So why is it that all my Amazon packages arrive with all that brown paper smushed up inside? That is to increase any contact time. It's like a crumple zone, which reduces the total force. Make sure if you get questions asked about these, you're talking about contact times, but you're talking about impulse and rates of change in momentum and force as well. Not just saying it increases contact time, because that doesn't tell enough normally to get you all of the marks. We're at the bottom of the page, so I want to keep running things out. And I also want to make sure I don't draw over under my face again. I got told off for that last time. So elastic and inelastic collisions. So we've got momentum and kinetic energy that we haven't really talked about yet. But momentum is always conserved. We could draw a table and everything. Momentum is always conserved. There's no situation in which momentum is not conserved. For kinetic energy, then in an elastic collision it is conserved, and an inelastic collision is not conserved. So inelastic collisions are things where there are crumple zones, sticking together of two objects. Elastic collisions, collisions between atoms, ions, electrons, etc. We call those elastic. And then snooker balls, but it's an approximation. Hi, child. Yeah, I'm starving too. Huh? I know, I'm going for 2 hours. Awesome. You know you're on stream, right?
Yeah, hi.
Hi.
I get 4 hours, so doubling it, unfortunately.
I'm not doubling it.
She doubles it.
Different rules.
It's learning.
And I doesn't double it either, I don't know what she's talking about.
I do it for extra studying. Sort of thing.
Anyway, the children have come to make me some lunch, which is nice of them.
You? Making you food.
Where did we get to? We did this one. We did this one. We did this one. Look at this one. Explosions are cool because we know that things, momentum's conserved. So if I have a bomb, or let's call it a bomb. Let's do a neat little bomb like this.
I got it.
If we've got a bomb and it explodes, let's say it explodes into exactly 2 pieces. One moves away like this, and one moves away like this. Then let's call this one A and this one B. MA, VA, and MB, VB have to be equal and in opposite directions, because here momentum equals 0. So here 0 is going to have to equal let's take right to be positive, MB VB minus MA VA. This is the reason why I do little flicks on my V's, because that could be a U. Appreciation of momentum conservation issues in the context of ethical transport design. I really don't know what this is talking about. Yeah, I'm not really sure what this one's talking about. Any clues would be great. Ooh.
Stop.
Oh no. I've rubbed out part of materials. That's no good, is it? Okay. Work, energy and power. Energy transferred is the same as work done, which is the force on an object. Oh dear. I know, I don't know what saying oh dear at. There's so many things going on which could be oh dear. Like my children melting cheese over everything, I imagine. Right, so if I've got a force in this direction, and my object is moving a distance, let's say it moves a distance d, in fact, let's say it moves a displacement s, then the work done would be the force multiplied by the displacement. Are you kidding? Ro, get your foot out of the way. The work done would be the force times the distance moved in the direction of the force. In this case, these two are parallel, so there's no issue. But if I were to move my force like this, then the only part of the force I'd be worried about would be F cos theta. So I'm only worried about the part of the force which is in the direction of the displacement. If I've got frictional forces, then some of the work done will be transferred to thermal energy, and some of the work done will be transferred to kinetic energy. If there are no frictional forces, all of the work done will be transferred to kinetic energy, because we have conservation of energy. Energy can never be created or destroyed. We can always figure out where the energy must have gone. If I do this much work, and say we do it in the time t, then power is the work done per unit time. It's always the rate of doing work, or the rate of energy transfer, and that never changes. Got delta W over delta T. In this case, if we ignore angles for a second, if we have F S over T, so Fs is my work done, and S over T is velocity, force multiplied by velocity is the same as power, which is the same as the rate of doing work, or the rate of energy transfer. Quantitative questions maybe set on variable forces. So you might need to figure out average forces. So the significance of the area under a force displacement graph. Let's have a look at that one. So if I've got force displacement, so we've got a constant force for a displacement. The area under here would be F times S. That would be the work done. So over here this is work. Efficiency, useful output power over input power. You can express this as a percentage or decimal Ideally not a fraction. Don't like fractions in physics. So if I got a useful out divided by my total in, so in these cases, if I've got some force multiplied by some displacement, and actually don't get all of that out as kinetic energy, then I'd have some amount less useful output than what I put in, probably due to friction in this case. But you can use that in a plethora of contexts, and again it's another one you'd want to be checking past paper questions for. Principle of conservation of energy. Energy is never created or destroyed. Ro, can you stop making noises so you can hear yourself on stream, please? This is. Only, I'm going to call it transferred to other forms. So we've got, for uniform gravitational fields, we can use changing gravitational potential energy. So we can call that GPE if we like. Gravitational potential energy is mg delta h. I actually prefer the p subscript. And then kinetic, so it's the mass times the gravitational field strength, which you figured out earlier was 9.81. It's actually newtons per kilogram, but either way. And then delta h, which is the change in height. So we can start at any point and go to any point as long as we're in a uniform gravitational field like we've got at the Earth's surface. And then our kinetic energy, or E subscript k, is a half mv squared. If I've got a falling object, it starts with 0 kinetic energy. But has some GPE. Down here, my GPE. Well, right, hang on, let's do that slightly differently. If I've got some gravitational potential energy up here, then down here, my kinetic energy equals my change in gravitational potential energy, assuming no air resistance. And these kind of things you can apply to just a lot of different situations. So we've got conservation from gravitational potential energy to kinetic energy, so when something's falling. If you've got something on a slope, then we're worried about the change in height of the centre of mass. That would be our change in height. So our change in gravitational potential energy would be that. If it's a frictionless slope and there's no air resistance and all that, then this change in gravitational potential energy would be the same as the change in kinetic energy of the thing sliding down the slope. If there was some friction, then we would lose some of that energy to work done against resistive forces, and it would become thermal energy, heating up the surroundings and all that good stuff. Speeding up now, we're nearly there. I don't need to rub this out. Now we could have an issue. Let me just quickly find those bits again before we move on to materials. Let's just make sure we've got all of the bits without them being rubbed out. Not sure what you're going to see on the screen now. Probably nothing changing. Pam pam. Just put that one over there. And we're good to go. So, that was all of mechanics. Crazy. The second part of this topic is materials. It starts off nice and straightforwardly. Interestingly enough, it doesn't ask about density of alloys. That's okay. So density is the ratio of the mass of something compared to its volume. So density, that's rho, Greek symbol rho, is mass over volume. And you may well be asked to do things like the volume of a sphere for the volume, or the volume of a cube, or anything else. They've got some in the front of the data book. You should always be able to find equations for those, for geometric shapes. Oh yeah, plus 12. I'll put it back on. For density, the units are going to be kilograms per meter cubed. We haven't talked a lot about units throughout all of this, sorry about that. But they're pretty important. We have talked about them throughout. Of course, as we've gone along. If you've got any questions about units, don't hesitate to ask. Drop a comment down below. That would be for later though, not for now. It's back on. It's back on. I don't know. We've kind of got two little sections left. Hooke's law and elastic limit. Okay, so let's talk about Hooke's law. If I have a spring, springs are nice because they tend to obey Hooke's law, and I apply a load to my spring, let's call that F, a force F, then the extension of the spring is equal to the spring constant, oh no, the force is equal to the spring constant multiplied by the extension. So the extension, if it had an original length which looked like this, the extension delta L would be the difference in length. We'll call that change in length. K is our spring constant, which is a ratio of force to change in length, so it's going to be in newtons per meter. Stiffer springs have higher spring constants. So if I've got a graph, so this is one of the odd graphs where actually we'll probably change the force. If we add force, then we get different extensions, but we're going to switch the axes. So we've got our independent variable on the y-axis and our dependent variable on the x-axis. If a substance is obeying Hooke's law, then we get a straight line. So then the gradient would be the spring constant. So we could rewrite this as y equals mx. If we plot the extension, this one would be in meters, we're using a slash, that would be in newtons. So something with a higher gradient would have a larger spring constant, which would mean that for a bigger force we get a smaller extension. So there's a higher spring constant, higher gradient of a force extension graph, stiffer the spring, and then for a lower spring constant, so a less stiff spring, you get a larger extension for a smaller force. So that's the relationship between the spring constant would be a value, and stiffness, if we didn't have a spring, K would still be the stiffness. Tensile strain, stress of a strain, let's do it like this. It's going to be the change in length over the original length. Oh, we've missed something quite important. On this graph here, this quantity is the force multiplied by the change in length. That's the work done in stretching the spring. So actually in this case with a spring, the work done in stretching the spring, if I were to unload it again, is the work that I get back if I unload the spring. In other cases that's not going to be the case, we'll talk about that. The elastic limit, so if this one here were to start bending over like this point here would be the elastic limit. So that's going to be where if you unload it, it doesn't go back to its original shape. So here it's behaving elastically, which is different to elastic collisions. But elastic means, well, it's not different to elastic collisions because we're going to get all the energy back that we put in. So we've got this region here, which is a straight line. Our elastic limit is when it bends over, and after this point it's been permanently deformed. So when I unload it from here, it's not going to go back to its original length. If this is its original length or not. And in that case, the work we get back will be, let's do this in different colours. So this section here and this section here, that would be the energy we get back. And the red section would be the energy lost. So when if we stretch something and it extends, it doesn't go back to its original length. Some of that energy has been used in changing or deforming the object. The total energy, if we add those two together, that would be the work done to stretch the thing. Right, let's get rid of all of this. Talk about stress and strain. So both of these are tensile stress and tensile strain. So this is when we stretch things. For a spring it's the same if you squash it. So my stress is going to be the force divided by the cross-sectional area. And then strain is going to be extension over original length. So if you're defining these, you need to make sure that you're including cross-sectional area and original length for a second mark. But the next point down here, we talked about it being the area under a force extension graph. We have a graph like this. What we didn't talk about is, if this is F and this is delta L, then the area under this triangle, so the energy transferred, is going to be a half F delta L, which is a half base times height. Plastic behaviour would be this section that I said when it bends over here. So plastic behaviour causes permanent deformation, so it doesn't ever go back to its original length. Fracture would be when it breaks. Brittle, so a brittle substance wouldn't have this section here. So brittle substance would fracture with no plastic deformation. This bit here is a bit we did earlier, where we've got the work done underneath the graph, and if it bends, we'd have the work done to deform, or the energy used to deform the thing, and then we'd have the energy that we put in, being elastic strain energy, and then the energy that we get back, well, the energy we get back with elastic strain energy to deform, would be that difference, and then the total would be the work done in stretching all of it. Spring energy transformed to kinetic and gravitational potential energy. Not entirely sure what that means. I'm going to look that up quickly. Spring energy transformed to kinetic and gravitational potential energy. Anybody got any questions? It's been quiet a lot. 12:19. Is anyone watching still? It's a good question. Still 8 people watching. I'm guessing it's talking about if you change that energy, so this energy that we've had from stretching our spring, if you then released something using that energy, then you could transfer the elastic potential energy to kinetic energy. Or if I had something which fell onto a spring, and then the spring compressed, then the GPE up here would all be, to the GPE would equal a half F delta L. Appreciation of energy conservation issues in the context of ethical transport design. Again, what are they talking about? Maybe we'll find out in summer. Eek. What are we looking at now? We're looking at a month and 5 days. Ooh. Ivy, can you take Minnie out, please? Now, our stress strain graphs. So remember, stress is force over area, and strain is extension over original length. If we've got so stress is actually proportional to force, and strain is proportional to extension. So they're going to look quite similar to our force extension graphs. If I've got a spring, my stress strain graph is going to look like this. That would be for elastic deformation. If I've got, let's say, something similar, but then it tails off like this, and there are other more complicated shapes. This could be for a wire. This one would be for a spring. And the gradient of these lines is related to the spring constant, but it's actually going to be the Young modulus. But that's in the next section. If we had something that looks like, hang on, this would be for a ductile material. In fact, let's not call that spring. Let's say that's for a brittle material. So here is where it fractures. This one fractures here. This is the ultimate tensile stress, so the point where the stress is the highest. This is our limit proportionality, or our elastic limit. And we've got one more shape that we need to know for these, and it's something like that. So this is a polymeric material. Like an elastic band, and if we unload each of these, we get different curves. So if we unload this brittle material, which has had no plastic deformation, it just moves up and down that line. The stress and the strain are proportional to one another. This one, if I have my wire or my ductile material, it's going to go back to the x-axis straight down elastically, but not go back nu L. And then my polymeric materials are really weird. They're going to go back like this, still end up at the same point. So the reason these are weird like this is because we're stretching and breaking sort of cross-link bonds, and we're changing the nature of the tangled polymer molecules. When we stretch it and then we pull it back together, they tangle themselves up again. That's the way they like to be. That's all of that. One more section to go, everybody. The Young modulus. So we've got tensile stress over tensile strain. So remember that stress was force over area, and that's all over strain, which was extension over original length. So this is a fraction under a fraction, so this one goes up to the top, so you get FL, and then this is a fraction under a fraction, or the top of a fraction under a fraction. This is just this divided by this, so that's going to be A multiplied by delta L. And the Young modulus, we can talk about units up here. So the units for stress are going to be pascals. Finally, I know, 2 hours and 20 minutes are going to be pascals, and units for strain is a length over a length, so there are no units for strain. So if we've got stress over strain, that's pascals over no units, so the Young's modulus has units of pascals. If we're using stress strain graphs to find the Young modulus, if we go back up, oh, let's not go back up because it's a mess. Let's talk about it down here. Then the gradient of a stress strain graph gives you the Young's modulus, or the Young modulus. And that's it. We won't talk about required practical 4, but we probably should. Things like using a fiducial mark. Maybe I'll do another live stream for all the required practicals. Ooh. Maybe, maybe not. This has been a long one. That's the end, I believe. There is no more. So materials looks quite short, but it's quite important. Mechanics is very long, but there's a lot of transferable skills in here, all the way through the second year. So units, vector scalars, the things like differentiating displacement, to get velocity and differentiating velocity to get acceleration, things like that. Tired Ash is one of. Why am I tired? But it has been. Let me look at the YouTube dashboard. 2 hours and 22 minutes. That's long. 6 people left watching. Right. It's been a pleasure, everybody. I am now Hank Marvin Starvin. I've been yawning. I know that's awful. I'm always yawning, Jack. I never get enough sleep. I've got a 17-month-old baby. Any thoughts about future streams or future videos? Anything you'd like to see next? All 6 people watching. I know one of those people is my son, who isn't actually watching. Thermal physics. Could be onto a winner there, Jack. Is that the next thing? You're right, circular motion. Thermal physics is alright, isn't it? It'll be a short one. Maybe it'd be nice to do a short one next. Well, Sasha, that is a good question. I'm hoping yes. Practicals might be a good one to do. Lots of ideas. Lots of ideas. Right. Thank you, everybody. I am now going to sign off. It's been a pleasure. I hope it's been really helpful. Cheery bye.